I'll do it from the point of view, not of my 95 TASI lectures, but from which is the first review with Interrogator, but from a point of view which is similar to the second review I wrote with Interrogator, or precisely that Interrogator wrote and I signed. And okay, so that's what I'll do. I'll have to be brief because there's no way I can do that in 2 hours and 30 minutes. Having said that, I do encourage you to ask as many questions as possible. Even if I go slower, I feel you get more out of the talks by asking all these questions. So we'll start with questions about last time. It was all clear? Everybody did the problems? Okay, so shut your notes, get an empty piece of paper. There's a quiz. No, we won't do that. So we started discussing SUSY QCD. This was an SUN gauge theory. With NF flavors of quarks. Where these are in the fundamental representation and these are in the anti-fundamental. And they have color indices and flavor indices. And I'll also denote them as matrices. We'll have Q and Q tilde. They have flavor and color indices. And then there's a potential for them. And the potential is sum of dA square, where dA is Q TA Q dagger minus Q tilde star TA Q tilde transpose. So for the notation is that the color index for Q is the second index, so it's contracted with TA, and therefore for Q dagger it's the first index. One of them has an upper index, the other is a lower index. For Q tilde, it's reversed. So here we need to put a complex conjugate to put it in the fundamental representation, and the minus sign here is because the TAs are the conjugate representation. So that's the potential. And it turns out that this potential has lots of flat directions. For example, imagine the group is actually not SUN but UN. Imagine N is 1. There's only one flavor and one color. Then we can just give a VEV to Q and a VEV to Q tilde, thus canceling these two terms. More generally, the kind of flat directions we find depend on the number of flavors and colors. So again, what I emphasize here is that when we study quantum field theory, the first thing to do is not to study the quantum field theory, but the classical field theory. And until we have complete control over the classical theory, we shouldn't even begin to think about quantizing it. So again, there are simple things we should do classically, and they usually give us a lot of insight, which people tend to ignore. So we'll start with the classical theory, and we try to solve the equations, all of these equal 0. And this is a bunch of algebraic equations. There are various ways of solving it. For example, you can use the symmetries to simplify the problem. There's a lot of symmetry. There's a color symmetry, and there's a flavor symmetry that act on Q and Q tilde. And the solution looks different depending on what the number of flavors and the number of colors are. So if the number of flavors is less than the number of colors, the most general solution of this D-term equation can be written as follows. So the Q's are rectangular matrices. Recall the color indices going this way, and the flavor indices going this way, the color indices going that way. This is the notation I use here. And you see that this matrix has more colors than flavors, because this is the case I'm talking about. And V1 up to VNF are arbitrary complex numbers. This is not the most general solution. The most general solution is this up to symmetry transformations. And the symmetry transformations act on Q and Q tilde. The color transformations are matrices multiplied from the right. And the flavor symmetries are different for Q and Q tilde, and they act from the left. Is that clear, or should I explain that? No? Know that I shouldn't explain, or know that it's clear? Sorry? One more? Okay. So I denote Q and Q tilde as rectangular matrices. Color running this way. and flavor running this way. Such that here, for example, I really contract the color indices. And then the dA here, I also need a trace. Okay? That's in order to contract also the flavor indices. Yeah, I have it right in my notes. So how does flavor act? Flavor acts separately on Q and Q tilde, and they act on this index that labels the rows. As such, acts from the left. Color acts on these indices, and such it acts from the right. And Q and Q tilde are subject to separate independent flavor matrices for the symmetry, but the same color matrix. You have any discussion of quiver gauge theories in this school? No? Okay. So this is the most general solution. And what's the physics of this solution? See, if we take a generic point V1 up to VNF, every one of these vevs breaks the gauge symmetry. And the original SU NC gauge symmetry is Higgs to SU NC minus an F. Because every one of them breaks the symmetry one step further. And if this is 1, then the symmetry is completely broken. If this is 1, there's no SU1, so the symmetry is completely broken. So the low energy theory is an SUNC minus an F gauge theory. This is the unbroken group. Plus various moduli. And what are the moduli? The moduli are these complex numbers which can be changed up to flavor and color transformations. Color doesn't really act in the low energy theory, so there must be a gauge invariant description describing the moduli. So there are moduli, which are these NF numbers up to the symmetry transformations, and they can be parametrized in a gauge invariant fashion by a matrix of mesons M, which are Q tilde Q transpose. And to write it in components, M A tilde A. These are flavor indices. A is for the Q's and A tilde for the Q tildes. And this can be written in some detail as QAI, QIA. And I ask you, what does A correspond to? What does it label? The index A? Close. I think I heard the right answer. The color index, yeah. So I is the color. And notice that it is contracted such that this object is gauge invariant. In fact, this is a theorem in mathematics that was understood, I think, in the 18th century or maybe 19th, getting close to the time I was born, that whenever we have a situation like this with D terms, of course, the mathematicians didn't call it a D term, D terms equations. If we solve these equations and we divide by the gauge group, mod out by the gauge group, then there is always a way of describing it as holomorphic polynomial in the fundamental fields. Oh, yeah. But I asked about I, not about A. So you don't dig yourself deeper. These are the flavor indices. I hope I got it right. There's another notational confusion here that Q is the quark, and Q is also the supersymmetry generator. But I'm not going to do anything about that one. But thank you for pointing that out. Okay, so this is what can happen here. So the light fields are these moduli. There are NF square of them. And the gauge fields of this unbroken gauge symmetry. The situation is somewhat different when the number of flavors is larger or equal to the number of colors. We still need to solve these equations, the D-term equations. And the most general solution looks as follows. Q is again a rectangular matrix, but now it's tall and thin because there are more flavors than colors. And there are numbers here, V1 up to VNC, and 0 down here. And Q tilde is the same things with tildes. Zero. And again, we can, and there is a condition that VI absolute value square minus V tilde I absolute value square is independent of I. And you can take it as an exercise to check that these are indeed the most general solutions of these D-term equations up to symmetry transformations. Unlike this situation, here the gauge symmetry is completely broken. And this phi will be both the chiral superfield and the empty set, and I apologize for this notation. So what are the light fields? The light fields are the moduli. And we can count how many there are. We started with NF times NC times 2. These were the Qs. NC square minus one of them are Higgs in the Higgs mechanism. So they got mass. And the remaining ones are massless. How can we describe them? Again, there ought to be a description in terms of gauge invariant variables. So we can use the same meson that we had before, Q tilde Q transpose, and I will not bother to write it with the indices. But in addition, there are other gauge invariant polynomials we can write. So this is like a meson because it has a quark and an anti-quark. The other one is like a baryon, which has indices flavor 1 up to flavor NC. And it is epsilon I1 up to INC. And now we have the quarks, which have I1 to F1, Q, I2, F2, Q, and INC up to F and C. And I use the notation F for the flavor index to avoid the notational conflict. And we can similarly write the antibaryons. Notice that these are like baryons because the color is contracted antisymmetrically, and there are NC of them. So we take NC quarks, multiply them together, and we make a separate question. Why don't we have such an object here? After all, in ordinary QCD, we can make baryons even when the number of flavors is less than the number of colors. So why can't we write such an object in this case? This is an exercise for you. Yeah? There was a question here? Somebody raised his hand? No. So I said we can count how many fields there should be. We started with 2 NF and C quarks. We subtracted those that are eaten, NC minus 1. And what I wrote here is way, way too many. Already here in the mesons, we have NF square degrees of freedom in M. And already that overdoes it. There are too many mesons. So they cannot be all linearly independent. And that's easy to check. Indeed, the matrix M, so we contract the color indices. We are left out the flavor indices. So this is an F by NF matrix, but its rank is restricted. So the matrix M is not an arbitrary M. You are not allowed to specify arbitrary entries for this M. And this just follows from the fact that this meson was constructed out of these Qs. Take Q, it's a rectangular matrix. You multiply 2 rectangular matrices, and the rank of the resulting matrix is restricted. Is that clear? This is linear algebra 1 or something. Sorry, if I?
If I make a flavor transformation of Q, they are considered different moduli
That's right. This is a different point. Gauge symmetries, one should identify the points. This is actually an important point. Gauge symmetry is not a symmetry. When people call it a gauge symmetry, they generated an unnecessary confusion. Gauge symmetry is not a symmetry. It doesn't act on the states. You don't have a state in the Hilbert space and another state differing from it by a gauge transformation. So gauge symmetries do not generate, are not a symmetry. They don't act on anything. Unlike flavor symmetries. So if two different points in the modular space are related by flavor symmetry, these are distinct points which have the same physics. But these are distinct points. 2 points which are related by gauge symmetry are not distinct points. They should be viewed as the same point. So that's the first restriction. So if NF is bigger than NC, you see the matrix M is restricted. But even if NF equals NC, there are further relations. So there are further relations in addition to that in terms of these B's. For example, for NF equals NC, this restriction on the rank doesn't tell us anything. But B and B tilde are flavor singlets because the number of flavors is the same as the number of colors. We contract all the indices antisymmetrically. And in this case, you can check that the determinant of M equals B tilde. B and B tilde do not carry indices. And this is just a property of matrices. That the determinant of Q tilde, Q transpose, is the same as B tilde, which are essentially the determinant. B is the determinant of the matrix Q in this case, and B tilde is the determinant of the matrix Q tilde. So if you count how many degrees of freedom we have here in the matrix M, there are NF square or NC square. It's the same in this case, degrees of freedom in M. One more in B and one more in B tilde. But we subtract one because of the relation, and that should agree with the number of moduli which are not eaten, the number of light fields which are not eaten, which are the moduli. So in this case of NF equals NC, so I'll continue in here, the modular space of vacua is the space of all M's, B and B tilde, subject to the condition that M equals B tilde. For NF less than NC, the modular space is just a space of M's. And for NF bigger than NC, there are many more relations, and it's getting a little bit more complicated. But there's always a way of describing it in terms of M and B and relations. So what have we done so far? We looked at the classical theory and just analyzed the question, where does the potential vanish? Where does it vanish? So this is a problem you can give somebody, a freshman. Right. Here is a function of many variables. When does it vanish? It's a set of algebraic equations, and this is the solution. No physics in this. The physics is that at different points on this space of solutions, the physics looks different. The gauge symmetry is broken, the gauge symmetry is broken less. We can, the light degrees of freedom include gauge fields and do not include gauge fields, etc. But all this is classical physics. Okay. Now we're ready to move to the quantum theory. So the first thing we do is perturbation theory. And again, perturbation theory is boring, but it's excellent. Perturbation theory gives us a lot of physics. What happens to this structure I talked about here in perturbation theory? Answer, nothing. All the modular space of vacua remain there. A non-renormalization theorem similar to the one I proved in the first lecture here is valid here. There is no superpotential you can write down that would lift the degeneracy. And we have this modular space of vacua, classically. What happens quantum mechanically, non-perturbatively? Non-perturbatively, the situation is a lot more interesting. So I'm going to take a somewhat unusual route to the non-perturbative theory. And what we'll do is make the theory simple. We'll make it simple by giving masses to the quarks. So I'm turning on a 3-level superpotential. I think I've already mentioned that I can do that yesterday. Trace. And the color index goes here. So it's M, Q, Q tilde, and I think I need a transpose. I must put it somewhere in my notes. Yep, I need the transpose. So I turn on this master. Or in the pure gauge theory, when the number of flavors is 0, I don't even need to discuss that. So let's start with discussing the theory without flavors. This is a pure gauge theory, no flavor. So I'm not going to prove it here. I just state the answer. And so the logic will be a little bit circular, but all these gaps can be closed. I'm going to postulate one fact and derive a lot of physics from this fact. And later we can go back and prove this assumption. So this theory has gauge fields and gauginos. This is the cast of characters. The gauginos are in the adjoint, and they interact using the standard gauge theory interactions. This theory classically has a U1R symmetry, a symmetry under which the gauginos are rotated by a phase, and that's all it does. This symmetry is anomalous, and the anomaly breaks it to a discrete Z sub NC symmetry. So classically, there is a U1R symmetry, and broken in the quantum theory to Z to NC, and that such discrete R symmetries will be discussed at length by Michael. That's what the anomaly does. And it's convenient to define an object S, a chiral superfield S, which is minus 1 over 32 pi square, trace W alpha W alpha. And I'm using Wesson-Bagger notation. And this thing starts its life, and of the first term is 1 over 32 pi square, trace lambda lambda, plus dot dot dot, where the lambda is the gaugino. Now in the quantum theory, now comes the assumption I'm going to make. This S gets an expectation value. So this is 1 over 32 pi square trace lambda lambda. And it must be proportional to the dynamically generated scale of the theory, big lambda, this theory, raised, and I'm going to write it in a funny way. On dimensional grounds, it has to be the scale to the third power, because this is dimension 3. So this lambda is like lambda QCD, 300 MeV or so. And if you formulate the theory with the cutoff, then lambda is the cutoff scale, e to the minus 8 pi square over 3 NC G at the cutoff. You usually see not this equation, but the logarithm of this equation. This is the way it's usually written, because you say that the coupling constant runs logarithmically. So you say that 1 over G at the cutoff scale behaves like log of the cutoff divided by some scale lambda. But this is a more convenient way of writing it. So the reason I raise it to the third 3nc power here is twofold. First, it cancels the 3nc from here. And second, it highlights another point. This theory has a U1R symmetry, which is explicitly broken to Z2nc. This wave of S, or of trace lambda lambda, is associated with spontaneous breaking to Z2. Therefore, the theory has NC different ground states, which are related by a underlined global symmetry. So these are distinct symmetry vacua, which have identical physics, are related by a symmetry. And if they are related by a symmetry, the phase of the expectation value, lambda lambda, should change between one vacuum and the other. And that's why it's written like this, with a 1 over NC. So that's the second reason. So the different branches of this fractional power correspond to the different vacua, which are related by the discrete symmetry. Now, everything I said so far can be formulated in terms of an effective superpotential. What do we mean by that? We couple the theory to the only coupling constant was G at the cutoff. We replace it by the scale lambda. So the theory is characterized by a scale lambda. And energy of order lambda, there are all sorts of glue balls and glue bolinos and whatever. and there is a gap. There are no massless particles. And at low energies, all that is left are the n vacua, NC vacua. And if we make this lambda space dependent, we can also make it superspace dependent. If we do that, we can find an effective superpotential at low energies. So everything I said here can be summarized by saying that the effective superpotential is this thing. And I emphasize that there has to be an NC out front. And I would like to make a few comments about this superpotential. What does it mean and what is it good for? Lambda is a number. As such, a constant in the superpotential doesn't mean much in the gauge theory. So somebody could say, you know, I'm just confusing you here. Lambda is a number. At low energies, I have a vacuum, in fact, NC of them. And I write a superpotential, which is some constant. But the constant doesn't mean anything, so why am I confusing you with all this? Two answers to that. First of all, if we couple the system to supergravity, the constant in the superpotential does mean something, and therefore it's measurable. We started with a theory without this constant, and we generate a constant. Number two, if we make these lambdas not numbers, but superfields, kind of give it slight dependence on x and slight dependence on theta, then this is meaningful. Furthermore, we can use this superpotential to derive many results. Number one, the theory has NC different ground states. So imagine we take all of space and we divide it to two halves. They don't have to be equal. And say that we have ground state number K1 on one side and ground state number K2 in the other side. So nothing stops us from doing that. In between these two ground states, there will be a domain wall. So this is very typical in field theory. You can have you have more than one ground state. You can have two separate ground states from the two sides of the domain wall, and in between, there's some energy density, which leads to tension in the domain wall. Again, going back to your question, if the two vacua are related by a gauge symmetry, then they should really be identified, and then there is no domain wall between them. Since they are related by a global symmetry, there can be a domain wall between them. So in this case, the domain wall can be written, the tension of the domain wall, which connects vacuum with K1, vacuum with K2, is the difference between the superpotential in one domain wall and the other. I'm not going to prove this result. It follows from BPS, and you've heard many different related things here by other speakers. But I'll say that this is one use of this superpotential. So we can write this tension as the absolute value of NC, lambda to the 3NC to the 1 over NC. And we have two phases here, e to the 2 pi I K1 over NC minus the same thing with K1 interchained with K2. And we close the absolute value. So this is the tension of a domain wall. So this superpotential, in addition to being well defined, it also allows us very easily to compute tensions of domain walls, which is measurable. Yes? Which one? This one or that one? The one on the right? This Z2 is lambda goes to minus lambda. This symmetry is always there because it's really part of the Lorentz group. Right? Lorentz transformation, if I do a 2 pi rotation, all the bosons come back to themselves, but all the fermions flip sign. So this symmetry should better not be broken. And indeed, the expectation value of lambda would break it, but the expectation value of lambda squared doesn't break it.
One second, how did you break this symmetry?
This one?
Yeah, that one and you want symmetry.
Okay, this is explicit breaking. It comes from the anomaly. Anomaly tells us that the symmetry is not exact. I can give a whole lecture about that. This one is spontaneous breaking. The theory still has the Z2NC symmetry. It's spontaneously broken to Z2. So around every one of the vacua, the symmetry is not there, but the theory has NC vacua, which are related by the action of the symmetry.
Do you choose a vacuum by the expectation value of S?
Yes, there are NC. Sorry?
I didn't see how did you choose?
The thing here has NC branches.
Yeah.
because of the fractional power. And which branch you took, which branch you take, determines which vacuum you're in.
That breaks G2NC to G2.
Yeah. Because there are NC different values for the phase. Next, we can deform the theory. So we studied the theory with one value of lambda. We can ask, what if the value of lambda is slightly different? We even said that lambda can be viewed as a space-dependent object. So in most of space, we'll have one value of lambda, take some chunk of space, and deform the value of lambda. In condensed matter physics, you do it all the time. You have one temperature in part of space, different temperature in the rest of space. Some magnetic field here, other magnetic field there. So we'll have a knob that will allow us to make lambda a little bit bigger in some point. How do we do that? We add to the Lagrangian a source. So lambda can be viewed, or more precisely log lambda, so 3nc log lambda is the source for the operator S. How do we change lambda? When we change lambda, we change G, the coupling constant, and through the renormalization group, this log lambda is the same as 1 over G squared, and that shifts the Lagrangian by S. This allows us to derive the expectation value of S as the derivative of the superpotential with respect to this object. So it's 1 over 3nc d by d log lambda W effective. And indeed, if you take the derivative from here, this logarithmic derivative, you end up with this formula. So this is yet another interpretation of this formula. It is such that if we differentiate it with respect to log lambda, we derive the expectation value. This is very standard in thermodynamics, where we exchange sources with couplings, or in the first few lectures of quantum field theory or classical field theory, where we add sources and we perform a Legendre transform from one to the other. So we can perform a Legendre transform and find W effective of S by performing this Legendre transform, which is NC S 1 minus log S over lambda cube. And you can check that if you perform the Legendre transform between this and that, so if you perform Legendre transform on this, you find this. If you perform Legendre transform on this, you find that. This is a nice formula which has a lot of nice properties and also has a lot of confusing properties. The nice properties. We derived it from the assumption that S has this value. You can also show that this is basically the only thing you can write down which is consistent with the symmetries. And you see it's a very simple compact formula which has everything in it. You could take that as the starting point of this discussion. These are the nice things. The confusing things are more common in the literature. So I'll tell you now what this formula is not. This is a 1pi action for the operator S. This is not a Wilsonian action for anything. S is not a massless particle, number one. Number two, S is not even a massive particle. Some people call S the global field. I don't know what the global field means. And my problem here is not with global, my problem is with the. Which one? The spectrum has lots of globules. Maybe some of them are more stable than others. S is neither of them. S is some operator, which when we act on the vacuum, it gives you some state. And that state is a linear combination of states with globules and globolinos and what have you. It's a very complicated state. S is not a particle, and therefore it makes no sense to write a Kähler potential for S. If S had been a massless particle, we could have said, okay, S is what is called an interpolating field for a certain particle. This makes sense only when the particle is massless. And now we can write a Wilsonian effective action for this particle. And we do that using a field, S, and it has a superpotential and a Kähler potential and higher derivative terms, etc., etc. S is none of that. S is only this object. It's a composite operator in the theory. It has an expectation value, and we can write such a 1 pi effective superpotential, which has a lot of marvelous properties, but what it's not is a Wilsonian effective action. This is something very important. If you get one lesson out of these 4 lectures, this is probably it, because everything else is emphasized in many places. This is the only point which I think has the most occasions in the literature of the opposite statement. So this S, again, is not the interpolating field for every massless particle, and this superpotential is not a Wilsonian superpotential. Having said that, it's a wonderful object that allows us to derive all these things, and now I'm going to do all of supersymmetric QCD using this formula. So it's a wonderful object, but it's very important to keep its limitations in mind. In fact, I will show you how we can derive correct results from this, and I will show you how you can, if you are careless, derive wrong results from this formula. And I'll show where the pitfalls are. You're never confused about this issue, I know, Matt.
I'm confused about what you said. So if there is a 1 pi effective action, that also has derivative terms in it. What are we saying about those? That we're not considering them? That they're not to be effective?
First of all, they're not under control because they're not holomorphic. So the spirit of these lectures, we only do things which are under control. Then the other thing is we could do that, but it will be very sensitive to details of how you defined S. S is a holomorphic object, so for the superpotential, these things don't matter. Exactly how I regularize this composite object doesn't matter here as long as it has the right symmetries and right supersymmetry. For the higher order corrections, to the extent that they do make sense, they do depend on all these details. But it would be wrong to use these high order corrections and to compute the potential that would come from integrating out the auxiliary field of F using such a Kähler potential and this superpotential. This would be so wrong that it even leads to qualitatively wrong results and fundamental confusions in the literature. And the older people in the literature probably know what I'm talking about. The younger people, I think, will be better off not knowing what I'm talking about. Yes?
What meaning will you write down the derivative for an operator?
Well, that's exactly what it means. Doesn't mean more or less than this. This is a way to find expectation values for that operator. So this means exactly this, not more and not less. The fact that we can use it to do many things is nice, but that's the meaning of this.
The thing you took the Legendre transform of is a Wilson action.
No.
This one? I thought lambda is a superior.
If you think of lambda as a background field, yes. Yeah. But strictly speaking, the Wilsonian action is a number, and there are no light fields. So a low-energy observer would say, if lambda depends on space-time, this is what I measure. So this can be thought of as a Wilsonian action. And this Legendre transform cannot be. We will soon have examples where the analog of this can be viewed as a Wilsonian action. It will have dual interpretation, both as similar to this, it's kind of like the 1 pi generating functional for expectation values, etc., and the Wilsonian action. We'll have examples like that. But we'll also have examples where this interpretation is wrong. We'll have something which looks almost like the Wilsonian action, but it's not. And this is trivially not a Wilsonian action because S is not massless. Right? So we can argue what this thing is, but what it certainly is not is a Wilsonian action. If it's a Wilsonian action, at what scale? Yeah. Okay. I'm ready to introduce the masses. In fact, I don't need to introduce them because I've already done here. So we'll take the same story here, and we give the masses. And let's assume that the masses are huge. So this theory has some scale lambda. This is the scale where the dynamics become strong at low energies through a formula like the one I'm erasing now. And at energies way, way above that, all the eigenvalues of M are found. So the eigenvalues of M are much, much bigger than lambda. Let's take such a limit. How do we analyze this physics? That's easy. All the quarks are very heavy. Think of them as top quark. Has no effect on the dynamics of QCD. What do? We integrate them out. To leading order, just forget about that. And what we have below is the same SUNC theory that we had before. There's a slight correction at one loop that the scale of this low energy lambda, of this low energy QCD, is different than the short distance lambda. And I think we've seen that in some of the talk when people talk about coupling constant for normalization, I think in Michael's talk. Need to have lambda at low energies, G at low energy. One of the speakers here had it.
I will.
You will? So maybe I read your notes. Sorry for not paying too much attention during your talk. So the low energy lambda, the lambda of the low energy theory, to the power 3nc, it's always a good idea to multiply by that, is the determinant of M times lambda to the 3nc minus nf. Again, this formula is usually seen as the logarithm of this formula. Usually it's not written this way, but the logarithm of this formula. And then allows us to relate the lambda of the high energy theory, the short distance microscopic theory, to the effective lambda of the low energy theory. And the exponent here is the one loop beta function of the pure gauge theory. And this thing is the one loop beta function of the theory with matter. I think it was Matt yesterday who had a similar formula, which was a linear combination of NF and NC, but with different coefficients. Right? Did you have it, or was it again in the notes? But no. Yeah. He didn't have the numbers 3 and 1. He had different coefficients. Now, Matt didn't make a mistake. And I leave it as a question for you. Why did Matt have different coefficients than the one I have here? You can go through your notes and check the coefficients. They're different. I think they were different, right? Yeah. Why is it? Anyway, these are correct for our purposes. So we continue studying this limit, that the masses are very, very heavy. So what happens at low energies? At low energies, well below the masses of these particles, we have the pure gauge theory. This is our previous example. And we already learned what the superpotential is. We had W effective was NC, coefficient is important, lambda low to the 3NC to the power 1 over NC. And we can write that as NC, dead M, lambda to the 3NC minus NF to the power 1 over NC. I have to make a few comments here. Comment number 1. When I said before that the Gaugino condensate is lambda cube, this was the expectation value. Same expectation that appeared here and appeared here before I erased it. That was true with some definition of lambda. And this is a very convenient definition, which is known as dimensional reduction bar. If you and I use different regularization schemes, our lambda will differ by a multiplicative factor. So for ordinary QCD, if you might think you want to work on the lattice, you have some lambda which is convenient for the lattice. Somebody else will say, no, I don't like the lattice. I really like Pauli-Villa's regularization. So that person will have a different value of lambda. The difference between them is a multiplicative factor. So throughout these talks, I adopt a particular regularization scheme, a very convenient one, which is known as dr bar. In this regularization scheme, the prefactor here is also exactly 1. Again, somebody should have asked me here, take the log of this formula. We see things that we recognize up to an additive constant. An additive constant in the log is a multiplicative constant here, Which multiplicative constant did I use? I used the one in that particular regularization scheme. So this formula is exact in that regularization scheme.
After integrating out the massive parts, why don't we have a degree of massless gauge?
Why?
Why don't we have a massless
We do.
gauge degree?
So we now do two steps. First, we integrate out the quarks. This can be done, say, at one loop. All it did was to change the value of lambda. The low-energy theory has a new value of lambda and massless gauge fields. Now we have to analyze this theory, the second step. That second step is precisely the example I did before of the pure gauge theory. So I borrow the answer, not borrow, I take the answer from the previous. I don't borrow because I'm not planning to give it back. Which is this. The only thing is that I added this subscript L here, because that's not the full lambda of the theory, but only the lambda of this SUN gauge theory without matter. And then I substitute. This is a substitution. So we found this W effective. The theory still has a gap, no massless particles. If you wish, this is the Wilsonian effective action, which is just a constant. Depends only on the background fields. But we can play a game similar to this one. And we can think of M as being the source. So the same as before. 3, in this case, would be 3 NC minus NF log lambda is the source for S. And M is a source for big M.
Why do you say that there are no massless particles?
Well, at 3 level, we had massive quarks. We integrated them out. We have the pure gauge theory. And we postulated earlier, without a proof, that the pure gauge SUN theory, all these gauge fields and gauginos combine. There is a gap in the spectrum, and there is an isolated vacuum. In fact, NC of them.
But that we don't know how. Why?
We can prove it, but at this point, I'm not proving it. I'm postulating it, and I'm deriving results. Once we have results, I'll show you that this story can be run backwards and derive this. I made one assumption. It's actually 2. That the pure gauge theory has a gap, assumption number 1. And number 2, the gaugino bilinear has an expectation value. And I even told you what the coefficient is, so that the formulas are nice. And maybe this afternoon, we'll derive all these facts by running the story I'm going to tell you, but running it backwards. So let's accept that as an assumption and derive results. We will notice that not only don't we run into a contradiction, we get some beautiful story out of it, and also we'll get to one point where we can actually do a complete calculation and then run the whole story backwards.
Big M there is QQ tilde?
The same big M that we had before. It's the source, it's the same as this. Almost QQ tilde, it's QQ tilde transpose, which your thesis advisor is the one who got straight for the first time.
Question. So why the source for TASI is log lambda, not log lambda?
I'm sorry?
Why the source for TASI is log lambda, not log lambda?
It's the same. They're related by M. But more generally, we formulate the theory at short distance. At short distance, the theory is characterized by big lambda and little m. These are the objects which characterize the theory. By the time we flow to lower energies, there are some effective couplings which are functions of the short distance couplings. Like lambda L.
If you use the example before, like take log lambda L, it seems like the combination of log lambda and L.
But how do you change? You change the theory at short distance. How do you change the theory at short distance? You change G and you change M. Now, instead of changing G, you can write this object. This object is like 1 over G squared. Up to some pi's and the cutoff and so forth. So this is the finite object. It's 3nc minus nf. This is the 1 over beta function times log lambda. So you change the parameters at short distance. So this is what we do in physics. Physics is the following. We have some theory at short distance. We change the parameters. We are in the lab. We change the knobs. Or we play God on the multiverse, or whatever your favorite way of doing it. We change the parameters at long distance, at short distance, and then the goal of physics is to find the outcome at long distance. We throw particles in a box. This is the short distance formulation, and a superconductor comes out. That's the long distance answer. We put quarks and gluons in the box, and we formulate put some masses in G, some cutoff. It specifies the theory at short distance, and we flow to the infrared, and we find what we find. We put ordinary quarks and gluons in the box with some masses and some G, alpha strong, and so forth. And at long distance, we see pions and rho mesons and A1, and tau decays to neutrino and some number of pions and what have you. This is the answer to a question. So what do we do here when we change the source? We go back and say, well, let's change the problem a little bit. Change the parameters at short distance. How will that affect the outcome? This has been physics. This has been the way people thought about physics for the last few centuries. It's not new to TASI 2010.
So is 3nc equals to F a special?
Very special. But let's assume that NF is less than 3nc, so that we have asymptotic freedom. It's again similar to the statements Matt made yesterday, except that the coefficients here are slightly different. In the meantime, has anybody solved this problem of why the coefficients here are different than in Matt's talk? Thank you. Yeah, he did the non-supersymmetric case, so that's why the coefficients are different. So we play the same game again. We introduce these G's, these two sources, and that allows us to find expectation values. Here it is. So now we can find both expectation values of M and S using this formula, this derivative, taking derivative and writing the Legendre transform. So we can do Legendre transform for one of them, Legendre transform for the other, or Legendre transform for both. And what do we find? We find that the expectation value of M is the derivative of this superpotential with respect to, everybody is so alert this morning. Take the derivative, and this is that M, lambda to the 3nc minus nf. Let's see if I have enough room here. 1 over nc, and M is a metric, so here I have 1 over little m. Notice that without doing any work, we found the expectation value of the quantum theory of the meson M. Just by knowing something about the pure gauge theory and general principles of quantum field theory, we found the expectation value of the meson M, the analog of solving for psi bar psi in ordinary QCD. And we managed to do that without doing any calculation. And similarly, the expectation value of S is d by d log of this lambda to the 3nc minus nf of W effective, which is that M lambda to the 3nc minus nf to the 1 over nc. And we can also write an effective superpotential. So the first thing I'll do is write an effective superpotential for the fields by performing the Legendre transform. So let's perform Legendre transform only on big M, not on big S. We can do both. As I said, we can do Legendre transform on one, or the other, or both. And if you don't like that, or you don't remember, take your favorite thermodynamics book before you learned about statistical mechanics, just in ordinary thermodynamics, and you will see that you do it all the time. Do the Legendre transform with respect to the number of particles, but not with respect to the magnetic field, or with respect to the magnetic field, but not in terms of the number of particles, or you can add various other sources. It's exactly the same thing. So I'm going to write two effective superpotentials here. One is a function of big M, and the other will be for both M and S. That's actually important, so I'll try to put it so that I will not be limited by space. I'm already limited by time, so. So we take these formulas that we had there for the effective superpotential as a function of the couplings. And now we'll play the standard thermodynamics game and find the effective superpotential for the fields. So all I'm going to use is these two formulas. In fact, is this formula. Taking this, we can take derivatives and perform Legendre transform, and we find answers. So I have to hide it. So W effective of M turns out to be NC minus NF lambda to the 3NC minus NF over the determinant of M, all this raised to the power 1 over N C minus NF. And we can also write W effective for plus trace of little m, big M, which shows us how we integrate out. If you integrate out big M out of this formula, you will get the other one. So if you form the Legendre transform, you get this one. And the one which is a function of M and S is S NC minus NF. And you can do the algebra yourself. It's not that much work. Log S to the NC minus NF that M lambda to the 3NC minus NF, and we close plus trace little m big M. So everything I said today is summarized, except at the beginning of the lecture, is summarized by this formula, or that one, or the one in terms of the couplings. This is a tautology, because we go between them by just performing Legendre transform. It's like fixed number of particles or fixed chemical potential, grand canonical ensemble, small canonical, whatever it's called. These are all the same. Again, I emphasize, these are not Wilsonian actions. These are not Wilsonian actions because they do not describe massless particles. These are 1PI actions. Just one second. And okay, I don't remember what, so now you can ask, because you've interrupted anyway. Yes?
So I'm just a little confused. I thought you did a Legendre transformation with respect to lambda, but I see lambda here.
Log lambda. Yeah, but that's what you see. You see here the source. Let's collect the term with S. So you have S log lambda to the 3NC minus NF. So when you call Legendre transform, the question is whether you do or do not include this term. I like to include this term. The reason I like to include this term is that otherwise I can never remember when there is and when there isn't a minus sign when I try to do the inverse Legendre transform. When you do a Legendre transform, I think strictly speaking, you do not include this term and you do not include this term. But then when you do the inverse Legendre transform, there are various minus signs in the derivative. Sometimes it's with them. So I can never remember that. The way to do that is to add to the Legendre transform this term. And then you never need to remember the minus signs because you include the source in the effective action. And then you never write the derivative of the action equals something, but you just say the derivative of the action is always 0. When you integrate something out, the derivative of this effective action equals 0. And now you solve and you plug it back in. And then you never need to remember whether it comes with a plus sign or minus sign. You know which sign I'm talking about? Yeah. We differentiate with respect to the magnetic field. I think there's no minus sign. That's right. So there's an L there, but not the other way. Or I think when you differentiate with respect to the magnetic field, there's no minus sign. We find the magnetization with differential with respect to magnetization. There's a minus sign for the magnetic field. I can never remember that. So this is a quick way of doing it so that you never have to remember the signs.
Okay. You say if I set the derivative of that
To zero.
then I get the other thing.
Yeah. And if you don't include that, you have to say that the derivative with respect to S is, yeah. It's exactly the same, but it's just a quicker way of doing Legendre transform. So we said what this is not. I would also like to emphasize that this matrix M, so now I'm going to really highlight why this is not the Wilsonian action. So this action is, these two actions are very good if you want to find expectation values. And we wrote the expectation values here. My Blackboard organization today is a disaster. So the information here, here, and here is equivalent to the information here. And you can easily go back and forth between them by taking derivatives, substituting back in, and so forth. Yes, I think. Yeah. And then there's a question whether you do or do not include the J phi in the gamma of phi. I like to include it. I think people usually do not include it. But the answer to your previous question is that it's the analog of gamma of phi with the addition of J phi. Yes, absolutely. Take it as a problem. Okay, excellent question. Where are all the discrete symmetries? Where are all the continuous symmetries? The anomalous, the non-anomalous symmetries? It's a very straightforward exercise. We know how these symmetries act on the fundamental fields. Therefore, we know how they act on M and lambda. Sorry, on M and S. And now we should be able to check that this Lagrangian preserves the symmetries. In fact, this is the only thing that preserves the symmetries up to overall normalization. You could have started the story like this. We want to write this one pi action for S and M. And this action has to preserve the symmetries and should be holomorphic. What can it be? This is the unique answer. I deliberately went the other way because I wanted to show the dynamics that leads to these terms. Not just showing that they can be there, but that they are in fact there. But I would like to make one more comment here. The matrix M is a matrix. This is the Q tilde Q. And I emphasized before that it has rank at most NC. If NC is if the number of flavors is less than the number of colors, the rank is the number of flavors. If the number of flavors is bigger than the number of colors, the rank is the number of colors. This is not true here. This is a matrix with maximal rank. So the operator QQ tilde classically has a restricted rank. Now we see that its quantum mechanical expectation has the full rank. This really highlights the fact that this action cannot possibly be, where was it? This one. Cannot possibly be the Wilsonian action. Because imagine we make the mass very small. If the mass is very small, and we still use this action, then, okay, there's an M here, which looks like our coordinate on the moduli space. The light fields are the moduli, and therefore we find an effective Lagrangian for the moduli. This looks like a good candidate to be our Wilsonian effective action. Again, I presented this as a 1pi effective action. Now, let's turn off the masses, or make the masses infinitesimal. Now we go to the beginning of the lecture. Classically, we had this moduli space of vacua. And now we can ask, is there any effective Wilsonian superpotential on that moduli space of vacua? Well, this looks like a good candidate. It depends on the right variables. We said that this M, this quark bilinear, is a coordinate on the moduli space of vacua. And it's supersymmetric. It's invariant. It looks like it has all the right properties. But it cannot possibly be the Wilsonian effective action on that moduli space of vacua. For one thing, the determinant here is not restricted. In fact, in the expectation value, we saw that the determinant is maximal rank. whereas along the flat directions, the determinant is restricted. So what is the Wilsonian interpretation of these two objects? Well, here, it's clear that there cannot be any Wilsonian interpretation, because there is no massless field S. But there is a sense in which this equation can almost be made Wilsonian. This one can be made Wilsonian in some cases, but not in others. So this is the next topic I'm going to emphasize and discuss. Any questions about that? So in the remaining 5 minutes, I would like first to summarize what we did today, because I think the logic was a little bit convoluted. We started with the Pugh gauge theory, and we added to it quarks. First, we analyzed the classical theory. We looked at the classical theory, and we found that it has a modular space of inequivalent vacua, parametrized by various fields. Then we asked, what does the non-perturbative theory do? That was hard. So we started with the theory without gauge field, and we postulated these assumptions. A theory confines, there is a gap, and there is a discrete Z2 and C symmetry, which is spontaneously broken by the expectation value of the gaugino bilinear. These assumptions by themselves allowed us to derive the analog of this formula for the Pugh gauge theory, and correspondingly the expectation value of S. Then we added the matter, and we assumed that the mass of the matter is very large. So in the limit of large mass, we can integrate the quarks out, find at lower energies the Pugh gauge theory, which was the previous example. This theory is becoming strongly coupled. We use the result that we had there to derive these two formulas. In fact, we can use any one of them, this or this. Or this. They are completely equivalent, and going from one to the other is just a Legendre transform, a simple algebraic manipulation. And what we are going to do now is, okay, so that allowed us to derive expectation values of some fields. But it doesn't tell us really what the physics is when we make the masses smaller. So now we'll try to tell the same story when the masses are much smaller than lambda, and see, just 1 second, what the interpretation of these equations are. What's the interpretation? And the key thing that is going to be useful here is that once we have these equations, it's very easy to make the masses smaller. In fact, the expressions I wrote here in any one of the three starred equations, the three starred equations are equivalent to each other. So knowing any one of them, we derive the others. These three starred equations, and also the expectation values, which come from here, must be exact. They are completely determined by holomorphy and symmetries, the way I outlined, the way I described in my first lecture. So these three starred equations were derived when the mass is large, even derived the coefficient, and once we derive them, we know these formulas for every value of the mass, including when the mass is very small. And this is very typical in supersymmetric theories. You derive some answer here, then you prove that it's exact, then you change the parameters very, very far. The formula should still be correct. The physical interpretation is totally different. So our goal now, and this is what I'll do in the remaining 3 minutes and the remaining lecture this afternoon, is take these formulas, the three starred equations, make the mass very small, and ask, what is the physics that gives us this answer? This is a very unusual situation in physics. We know the answer. We ask, what's the physics behind this answer? And this is the question I'll answer in the remaining 3 minutes of what will be left of them after I answer Tom's question this afternoon's lecture.
Sounds like so far, before you drop the mass, there is no Wilsonian effective action because there are no massive particles around. There are no light fields.
Right. Strictly speaking, there isn't one. The only thing that exists is a slight generalization of the Wilsonian action, where I let the coupling constant depend on space or on superspace. Now there are still no massless fields, but I can ask what's the free energy or the effective potential or the effective action as I vary these fields. So there is still something that an infrared person can discuss. It's not Wilsonian in the sense that it does not have any propagating particles, but they are interesting numbers which can be calculated or measured. Once I will drop the masses, there will be a lot of massless particles, and then we'll have to answer the question, what are these massless particles? What is their relation to the fundamental massless particles in the theory? They might be the same, there might be a subset of them, there might be others, there might be new ones, there might be composites, and they could have symmetries, they might have new symmetries, older symmetries, and that we'll do in the remaining lecture. Any more questions? So I'm going to end actually 2 minutes ahead of time, and I'll ask the organizer for 2 more minutes. So this will be a borrow. I'll borrow 2 minutes from the lecture this afternoon.